Hello. Today we are talking about the derivatives of inverse trig functions. Now, we don't use inverse trig functions all the time, but we are going to have to know how to work with their derivatives. So I'm going to start by just talking about inverses in general. So when we talk about an inverse in general, there is a relationship between a function and its inverse. So on the graph that we have right now, we have just a function. And so what we're asked to do is graph the inverse of the function. So what we need to do is, I'm going to look at number 2 real fast. Number 2 says there's a property of inverses graphically. The graphs of a function f and the function's inverse are mirror images across the line y equals x. So what I'm going to do is I'm going to go ahead and draw in on my graph y equals x. So there is my line for y is equal to x. Now all I'm going to do is reflect the black curve that was already here over the line y equals x. I'm going to start up here at the top, and if I were to reflect that over the y-axis, I would end up, the line y equals x, I would end up over here. And so that would be that part of the curve. And if I keep doing that, the blue curve should be the inverse. And again, it's just a reflection over the line y equals x. So next we have a property of inverses, and I'm not sure if you remember that, but if I take the inverse of a function and I plug that into the function, okay, so it's like an f of g of x, except I'm doing the f of the f inverse of x. The output of that is just x. And guess what happens in the next one? If I take the function and I plug it into the inverse, so I do f inverse of the function, the result or the output is x again. So we're going to use that property in just a minute. Number 4, what's the difference between arctangent x and tangent inverse x? So let me clarify. This is red tangent inverse. This is not, okay, this is not 1 over tangent of x. And I understand the exponent here looks like it's trying to tell me it's 1 over tangent of x, but this is lazy mathematician speak for tangent inverse. Okay, just to clarify. So back up. The whole question was, what's the difference between this arctangent of x and this tangent inverse of x? Well, they are both inverses. I'm going to scroll down a little bit. And we pretty much are going to use them interchangeably. It is understood when we use the arctangent of x that we are going to make it a function. So let's look in the first box. So y equals arctangent of x is a relation. It is not a function because it does not pass the vertical line test. So here we have arctangent, which is the inverse of tangent. And if you were to tilt your head sideways, you would be looking at what almost looks like the tangent graph. It also would need to be reflected over either the x-axis or y-axis. But upright, you can see it does not pass the vertical line test. So that's arctangent. It has infinitely many branches. So these branches go on and on and on, infinitely many. And in the other one, tangent inverse with that -1 notation, that one automatically has a restricted domain, so we're only looking at the y values between negative pi and positive pi. Sorry, negative pi over 2 and positive pi over 2. So here is the y value is positive pi over 2, and here the y value is negative pi over 2. So you can see that we have restricted our branch so that we are only using the one in the middle that we had over here from arctangent. Now, this isn't vital information, just wanted you to have some background. And again, whenever we reference arctangent, it's understood that we are using the branch in the middle so that it will be a function. So let's get down to some calculus. Derivative of the inverse tangent function. So what we're going to do now is we're going to come up with this derivative, but we need to do it in a sneaky kind of way to fake it out, because right now we don't know how to find the derivative of tangent inverse. So we're going to rewrite it a little bit. We're going to be a little sneaky and make it into something we do know the derivative of. So let's start with, we have y is equal to the tangent inverse of x. Now, there was a property that we had talked about, and I said, okay, we're going to use this property here in a minute. So let me go back. I'm going to scroll. And the property I want to use is right in here. If I take f of the f inverse of x, I get x. And if I take the f inverse of f of x, I get x. Let's see, what could I do down here now, scrolling to this one? Oh dear. Sorry. So what can I do to this to get rid of this tangent inverse? Guess what? If I take the tangent of the tangent inverse, what happens here? A output is just x. Now I can't just take the tangent of one side only, so let's take the tangent of both sides. Now that's a legal move. I can do that. So once I have done that, let's rewrite. We now have tangent of y is equal to x. Now, although that looks a little uncomfortable, do I know the derivative of tangent y? Well, I should. And do I know the derivative of x? Well, I should. So we can actually deal with this with the calculus that we know. Moving on to the next page. So here we're going to represent the equation that we had. Let me rewrite what we had. We had tangent of y is equal to x. And we want to draw this as a picture like we did in geometry class. Okay, so back up. If I was dealing with trig in geometry class, I did not have a choice. I had to have a right triangle. And if I had the tangent of something, that something had to be an angle in my right triangle. So right now I know y has to be an angle. So I'm going to put y, I can put it anywhere I want. I'm just going to put it here. And the next thing I know is that the tangent is x. Now when I did trig in geometry, I always wrote it as a fraction. Trig was always a fraction. X over 1 is the same as x. And if you remember from geometry, tangent is opposite, the side opposite, over the side adjacent, which tells me the side opposite of the y needs to be called x, and the side adjacent to the y needs to be called 1. So right now, we have a right triangle with an x in there and a y in there. The thing that's a little unfortunate right now is I don't have this side of the right triangle labeled. So right now, I'm going to call that C. But I could probably figure out what that is in terms of x, so it's going to look a little yucky. So from here, I'm going to set up Pythagorean theorem. A squared plus b squared is equal to c squared. Now I'd like to find c in terms of x, which means there'll be x's in there. So I will take the square root of both sides. And so my c is x squared, my c is the square root of x squared plus 1. I'm going to now redraw this triangle with everything in it. So my angle is y, my side opposite is x, my side adjacent is 1, and my hypotenuse is the square root of x squared plus 1. Now, if that didn't make sense, pause the video here, take a look at it again. I know we're just using letters and no numbers, and that's a little confusing, but all we did was do a little bit of geometry here. Okay, so using your equation from number 1, and just as a refresher, that was when we translated to tangent of y is equal to x. So that equation is this. Find the derivative of both sides with respect to x, and be sure to use the chain rule, excuse me, or the inside-outside rule. So I'm going to rewrite this with some colors. I have the outside is tangent of the inside is y, and that is equal to x. So I'm literally going to take the derivative of both sides. And again, as long as I do the same thing to both sides of the equation, that is legal. So what is the derivative of tangent, my outside? Well, that is secant squared of my inside, that stays the same, y, times the derivative of y. So I can call that y prime or dy dx. I'm going to call it dy dx. I sometimes accidentally lose my prime when I write y prime, and I don't want to lose that here. So dy dx kind of sticks out a little bit more. Now I need the derivative of x. And just with our power rule, the derivative of x is just 1. So we have now taken the derivative of both sides. So let's move on to part B. I'm going to scroll down a little bit. So in part B, after you take the derivative, solve for dy dx. So I want to leave dy dx right where it is. And what do I need to do to get both sides by itself? Well, I need to take this side and divide by secant squared of y, and I need to take this side and divide by secant squared of y. So when I do that, I have 1 over secant squared of y. So I have now solved for dy dx. So for number 4, it says we're going to use our diagram for number 2, which I don't have right here. So I'm going to scroll down and quickly draw that triangle again. So in my triangle, I had y, I had x, I had 1, and then I had the square root of x squared plus 1 was my hypotenuse. So now what I'm going to do is I'm going to find dy dx. So dy dx is 1 over the secant, I'm going to write this in calculus-friendly terms, secant of y squared. Well, I don't remember any of that from my geometry days, so let's rewrite secant. Secant is 1 over a different trig function, which you should know. So this 1 over I have written is the top of my fraction I started with. The next thing I'm going to write is secant, which is 1 over cosine of y. And again, the secant was squared, so that whole thing is squared. And now I need to simplify this. My 1 on top is going to stay. 1 squared is 1, and cosine of y squared is cosine of y squared. And if I have 1 over a fraction, that cosine of y quantity squared actually moves up to the top. Okay, so little manipulation there, and let me rewrite that down here. Dy dx is now cosine of y squared. So from here, I'm going to go to my picture. I'm going to go right to my diagram, right over here, and I want to find the cosine of y. I'm going to write it on the side. So cosine of y is, from right triangle trig, that is adjacent over the hypotenuse. So I'm going to look at my triangle. My angle is y, the adjacent is 1, and my hypotenuse is the green, x squared plus 1, the square root of that. So let's write that. I have the cosine of y is 1 over the square root of x squared plus 1, and that whole quantity is squared. From here, I square my square root, and those are actually inverses of each other, undoing each other, giving me 1 over x squared plus 1. If you didn't follow that, pause the video here and try and go through it again, or rewind and watch that part again. I'm going to scroll down to number 5. So in number 5, it's kind of hard to see what we're doing, but we're writing the derivative of y equals tangent inverse of x. So y prime is going to be 1 over x squared plus 1. Now, you can do this for any inverse trig. We don't think you have to, but I wanted you to understand how you got this. And if you don't memorize something, you can always figure it out. So again, any inverse trig function, you can go through the same process to discover what the derivative will be. So on this page, I'm going to scroll down. We need to find the tangent inverse of 3x. So let me go ahead and talk about this, in terms of inside and outside. So my outside is tangent inverse of, and my inside is 3x. So this is what my function is. So my derivative is going to be 1 over, now up here we had x was squared because that's what I was taking the tangent inverse of. That was my inside, so to speak. But this time, my inside is something else. My inside is 3x. So I'm really going to have 3x is going to be squared. And then I still have the plus 1. So this is the derivative of the inverse tangent. And now I need to multiply by the derivative of the inside, which is 3. And you're welcome to leave your answer like this. Please pause the video if you need to go over that again. Next page. So what I have here are all of the inverse trig derivatives. Now, hopefully you will see some similarities. I'm going to scroll a little bit so we have them all. Sorry about that. Some similarities between them. So basically what I do is I memorize these. Well, you need to memorize all of them. But if you memorize these, let's look at the difference between the derivative of sine inverse and the derivative of cosine inverse. Here's the difference, a negative sign. What's the difference between tangent inverse and cotangent inverse? Right here, a negative sign. What's the difference between secant inverse and cosecant inverse? Right here, a negative sign. So they are the same with the exception of the negatives. So all of the co-functions have the opposite sign from the non-co-functions. So let's go ahead and do some examples. I'm going to scroll down. So here we have y equals cosine inverse of e to the x. So I have y is equal to, my outside is cosine inverse, my inside is e to the 3x, and I know what my derivative of cosine inverse is. I'm going to write it down just so we can see the similarities in what we're doing. Negative 1 over the square root of 1 minus u squared times du. So let's find this derivative. I know I'm going to have a negative. I know I'm going to have a 1 over. I'm going to have a 1 minus. And then I'm going to have something squared. Well, that something is my inside, which is e to the 3x. Then I need to multiply by the derivative of my inside using my chain rule or inside-outside rule, which is e to the 3x times the derivative of that inside, which is 3. So here we have the derivative of cosine inverse of e raised to the 3x. What I'd like you to do right now is I would like for you to try number 2. So please pause the video here and try number 2. Here's the solution to number 2. Please pause the video here if you had any questions. On to number 3. So this one is different because we are evaluating the derivative at a specific point. So we're going to do exactly what we just did. Then we're going to plug in x is 0 and hopefully get a number. So first thing I'm going to do is I'm going to write down the derivative of cosecant inverse. And then let me rewrite in my colors. Outside is cosecant inverse. Inside is negative e to the x minus 1. So let's find our y prime. And the derivative of cosecant is my negative 1 over the absolute value of my inside times the square root of my inside squared minus 1. So let's plug my inside in. Now I need to multiply by the derivative of my inside, and the derivative of negative e to the x is negative e to the x. So at this point, I can plug in my x equals 0. So now what I'm finding is y prime at x equals 0 is, so we're going to plug in negative 1 over absolute value negative e to the 0 minus 1, and then we're taking the square root of negative e to the 0 minus 1 squared minus 1, and then we're multiplying that times negative e to the 0. So to simplify that, we need to recognize what e to the 0 is, and e to the 0 is just 1. So right here, this is really just a 1. So I have a negative 1 and a negative 1 on top, which means I'm left with a positive 1. And then on the bottom, this is a negative 1 minus 1 in absolute value, and that's the absolute value of negative 2, which is 2. Over here, this is a positive 1, which means I have a negative 2 being squared, and negative 2 squared is 4. So I have the square root of 4 minus 1, and I can simplify that to 1 over 2 square root of 3. Next one. So what I'd like for you to do is this one. I would like for you to be careful. I would also like you to try this one. And remember, I'm going to scroll a little bit, to be calculus friendly. So please pause the video here and complete these two. So please check your answers, and in number 4, be very careful. It's not an inverse trig. Okay, it's just a straight secant. So if you need to correct something, please pause the video here and correct what you need to correct. Moving on, we have these two left. So I would like for you to try this one. So please pause the video here to complete question 6. Here is the answer to number 6. Finally, if you need to correct that, please pause the video here. Finally, I would like you to try number 7. You are doing this exactly like the tangent inverse that was done earlier, and I would like you to complete that and bring it to class. So this concludes the video on inverse